Hello, and welcome back to University of Montana Advanced Hydrogeology. Um, Today we're going to be lecturing, continuing our lectures on solute transport and solute transport mechanisms. And today we're going to start thinking about how flow of water moves solutes. So the first thing we're going to talk about today is advection. So advection that's crazy. Is the movement actually not movement, let's go transport. The transport of mass by fluid movement. All right, so this is the groundwater flow moving solutes along with it. All right. So here we've got, let's say, water flowing in a current, and our particles, our dissolved particles, are moving along with the water, right? They're being transported in the current. This process is advection. All right, so we can do a little bit of mass balance in our special representative elementary volume for advection. So remember, we're in a porous media here, and I'm drawing the grains big so that you don't spend so much time drawing grains, but remember that our REB must contain quite a bit of pores and pore space in order to be an REB. Probably quite a few more than what I'm drawing here. Okay, so let's consider flux in the x direction. So we've got groundwater flow coming in, Q sub x, right? And it's coming in at some concentration, C sub x, or C, all right? Now let's make sure that this, let's think about the units of Q over C. We did this already, but remember Q is the same as the discharge Q over the area A times C, right? And we said that if Q was in, say, meters cubed per time, right, per meter squared, and our C, this per meter squared is the area, and our C was moles per meter cubed, and we would get moles per meter squared per time, which is a molar flux. All right, so this is our advective flux. Is little q Darcy flux times C gives us, as long as C is in molarity, we get our advective molar flux. I'm going to call that JA for advection, and that's advective molar flux. All right, so we have QC coming in. All right, we have Q times C going out, which we could write as QC in plus D dx QC times delta x. All right. So remember, so this here, this guy is the molar flux in, and this guy here is the molar flux out. All right. So the total mass of solute in here, remember, was Ne. So that gives us the volume of water times C times V, right? That's the total mass. And our mass balance says the change in mass over time is equal to the differences in the fluxes in and the fluxes out. So it says Ne dC dt times delta x, delta y, delta z. That's volume. That's my concentration change with time. And that's porosity, right? Is equal to the flux in Qx times C times delta x delta y times delta z, right? Minus Qx times C times delta y times delta z minus B dx Q C delta x delta y delta z. And I combined a few steps there because we've been doing these kind of derivations enough that I feel like it's okay to do that. So these guys cancel out, and we get, and we can cross these guys out, and we get Ne C dt is equal to negative D dx QC. All right, and this is the advective mass balance in the x direction. All right. We can do this for all the directions, all right? And so I can write advection for all directions. As Ne dC dt is equal to negative d dx qc qx minus d dx, or sorry, y. And actually these q's are a vector field, so I don't actually need to put a subscript in there, but well, let's just keep it for now. Y c minus d dz qz c. All right, all good. Okay, so this is the advective flux equation for all directions. And what it says is that the change in concentration with time is a function of the gradient or the divergence of the flux field. Okay, let's focus in back on, let's consider flow in one direction. So let's consider one-dimensional flow with uniform flux. All right, and so what that means is that we've got a flow field we've got a flow field where groundwater flow is moving in a single direction, so single direction at a constant flux q sub x. So it's constant, right? So in that case, let's have a look at our equation here. And let's say that this is x naught, and at time equals 0, my concentration is equal to 0. But at let's write this out for me. So C x 0 is equal to 0, and C 0 t is equal to f of x naught. So some function of x naught. Okay. Sorry, not x naught, f of t. So what this means is that what we're saying is that we started off with a concentration at 0 at our inlet, and that the inlet concentration varies. So our inlet, where x equals 0, varies as a function of time. All right? Okay, so let's look at our 1D equation. So it looked like this, NE dc dt is equal to negative d dx q x c. All right. Now, if I have a uniform flux, that means it doesn't change along the x direction. So it's constant with respect to this derivative, so I can bring it out. So that gives me NE dc dt is equal to q sub x, negative q sub x, dc dx. And I can do one more thing here, and that is to say that dc dt is equal to negative v sub x, where this v is the velocity, the fluid velocity. If we remember that v sub x is equal to the Darcy flux over the porosity. All right. Okay, in this case, we can solve this PDE by method of characteristics. I don't want to get too deep into that, but it's just another way that we can solve a partial differential equation. All right, and we get this solution that says C of x t is equal to f of x minus v sub x t. All right, what does this mean here? This guy implies that the solution to advection only, it's just the inlet concentration delayed by the location divided by the velocity. In practical terms, what this means is, let's say that I've got a step change. So at x naught, right, my concentration at the inlet, my concentration went looks like this. It started off at 0. So we could have a step change in concentration. So just like all our other step changes, we might write this way. For C x greater than 0, T equal to 0, our concentration is equal to 0. C, X equal to 0, T, our concentration is equal to C naught. So this is a step change in concentration, all right? And what it means is that if we were to look at the concentration at some place, X, I don't know what we're going to call it, X sub S, right? The sampling location. Our concentration would look like this. It would start off at 0. And then at some point, given by T equals to X sub S over V sub X, this is time, this axis here. Right, so I'm looking at the concentration at a point, X sub S, over time. At this magic time, T equals to X sub S over V sub X. My concentration will jump up to C naught. And then continue there. All right, so this delay here is given by this time. I'm just gonna lasso this and pull it up here. Okay, so this delay is given by X sub S over V sub X. Bottom line, intuitively, if I have a one-dimensional field and I start putting in concentration at various, putting in solute at various different concentrations, the solute moves at the advective flux and moves along with the water, the same speed, and we just see the arrival in a delayed fashion, right? This curve, so this curve where I have concentration at a point, over time, this is called a breakthrough curve. All right, and we call it a breakthrough curve because it's the time it takes for that inlet concentration to move to our point, our sampling point, and break through. All right, and the important thing is with advection only, we get exactly the same concentration history that we saw at the inlet. And this is called plug flow or piston flow. Plug flow or piston flow. And that just means we get the same breakthrough as the inlet concentration, but delayed by X over V sub X. All right, so exact same concentration history that we saw at the inlet, it's just delayed. Plug flow or piston flow. All right, so that's advection. And so under advection, some major assumptions, or not major assumptions, what advection means is the transport along with the velocity. And if it's a uniform velocity and transport by advection along a single uniform velocity, we get this plug flow. And that just means that the concentration looks exactly like what was inlet, it's just been delayed. All right, so that brings us to our next topic, and that is what happens if we're in a groundwater system and we're never, ever going to have a uniform velocity? And I'm going to talk to you about that. So let's go back and recall our porous media. All right, and let's think about water flowing through porous media. So here I've got, these grains of somewhat irregular shape. I'll sort of make them pretty regular here. But remember that they're basically never this regular. And let me fix this guy here. Whoops. Let's think about water moving through here. And let's start off by remembering that the water can't move through the grains, right? The water's got to move around the grains. And so it's got to take this tortuous path through an REV. But we are considering transport sort of at the REV scale. So we think about flow at the REV scale, which means we're thinking of sort of a uniform kind of velocity across that REV. So each one of these individual streamlines has a different velocity profile. And it has to travel different lengths. So each streamline has a different length. And a different velocity profile. If I were to zoom in even and think about, say, flow through this pore throat. So let's zoom in and just look here at flow through this pore throat. Here's our red box now at a different scale, right? And water's moving through here. Well, fluid dynamics tells us that we're going to have the highest velocity in the middle of the pore throat and the lowest velocity. This is my velocity profile, V sub x, within the pore throat. So I have a velocity of 0 essentially, right up against the grains. And I have maximum velocity in the middle of the pore throat. So I have a distribution of velocities even within one pore throat. So the bottom line is that, we think about flow at the REV scale. So at a scale much bigger than a pore throat, and one that includes many tortuous paths through it. All right. And so what we have this a huge distribution of velocities within one REV. And what that means, so the way we sort of handle this idea of scale, and the fact that what we're looking, when we're as groundwater scientists, we think about flow in sort of a cube, a representative elementary volume of porous media. And we're going to sort of assume that there's a uniform average velocity, not uniform, an average velocity through that REV. But we have to deal with the fact that stuff that's moving through there is actually is being moved by a whole bunch of different flow paths at a whole bunch of different velocities. So we can describe the velocity distribution within the REV in such a way that we say we say that the velocity field is equal to some average velocity plus a bunch of variations in velocity around the average, right? So this is our average velocity. And these are random fluctuations. Around so we might think about it in this way. So let's say that we were able to measure all these velocity variations, and we found an average, right? And so the average water's moving through here, say sort of on this path. This is an average fluid velocity path, and I came in and I measured right up here near the fluid boundary or near the grain boundary. Well, this would be a velocity that has a negative fluctuation added to it because it's slower than the average. Similarly, if I came through this big pore throat network with less tortuosity, this flow path might move faster through my REV than the green one. And we might say that this one we might describe as having the average velocity plus a positive fluctuation. So my velocity is faster, right? So this distribution of random velocities somehow describes the spread of velocities around our average velocity. So this is a distribution of velocities. Of velocity fluctuations. And we're going to say that we will never know what those all are, so we're going to treat them as a random distribution or a random variable that follows some statistical distribution. It's a random variable. Okay. So what does that mean? It means that if we were to add, say, a point source, so let's go back and let's draw some grains here. And let's say that, by some miracle, I was able to inject some solute concentration right here. What we would see is that we would have some of that solute going around pores. Some of that solute going around pores. This way, some of it going this way, this way, this way. All right, and so we tend to spread because of this tortuosity. So we inject it right here. Because of the tortuosity and because of these convoluted flow paths, because some solute might get sort of slowed down and move very slowly along here and then finally come out, all right, we see spreading. Oh. Yo, stop. We see spread of solute spatially. All right, so it spreads out laterally here in this case, but also because these flow paths don't all move at the same speed, all right, we're going to get some solute arriving very rapidly. Let's say that each one of these lines that I draw, I'm going over the same time increment. So some of them that had fast flow paths move very far. Some of them that had slow flow paths move not as far. We might get into some that have very slow flow paths. So over the same time increment, they only make it around a single grain, right? So we also spread solute in time, all right, or in its arrival time. So these random velocity fields spread our solute spatially, and they smear out the arrival time. They cause some of it to arrive quickly and some of it to arrive very slowly. So they spread it both in space and in time. And so this process of movement of fluid by random fluid velocity fluctuations around the mean, right? So we're going to say the movement of fluid or transport of solute by v hat, these random velocity fluctuations or this random velocity distribution that we don't know what is spread around our average velocity, we are going to call that dispersion. All right, and dispersion is this process of spreading by random velocity fluctuations. Now, if we assume a normal distribution. For V hat, all right? And a normal distribution, remember, would look like this. It's a bell curve. This guy here would be V bar. And this would be my probability. All right, and I'd have a bell-shaped curve of V hat around V bar. If I do that, it turns out that we can model dispersion looks like a diffusive process. All right, and that means transport by gradient. So let's look at what okay, so that means if we assume a normal distribution, then dispersion, we can show that dispersion is a diffusive process. And we have transport by concentration gradient, just like diffusion. And so we can derive Fick's law of, or we can not derive, but assume Fickian dispersion. All right, and that means that the flux, the molar flux, molar dispersion flux, all right, would be equal to N D, let's see, we need to get consistent right now with our nomenclature. So let me think about how I want to do that. I know what I'm going to do. All right, let's call this dm. We'll define it here in a sec. dm times dc. Do it in the x direction, dx. All right. Flux, the molar flux is equal to negative and the porosity times dm. We're going to define that here in a sec. Times the concentration gradient, where dm is the mechanical dispersion coefficient. All right, and this guy is due to V hat, right? Due to the random fluid velocity that we can't consider because it's beneath the scale of our EV. Right, and an important thing here is we've assumed something about this fluid velocity distribution. We've assumed that it's normally distributed, and we had to do that in order to get Fickian dispersion, which is convenient because it adds, because it looks just like diffusion. Okay, so I'm not going to belabor the dispersion too much yet. I think I'll save for another lecture getting way into the dispersivity and what it is. But let's say this, that here's the effect of dispersion. And let's start off. So let's recall our piston flow curve for a step change. Our piston flow breakthrough curve for a step change. So recall piston flow, i.e. advection only. Breakthrough for a step change at the inlet. All right, so remember that the concentration there, so this is the concentration, and this is time, all right? And our concentration, our piston flow curve looked like this. Came along at concentration equal to 0, and then at some time, we go straight up to C naught. So here's C naught. And remember this time here, the time lag was x sub s over v sub x, right? Okay, so even if we have a uniform sort of average groundwater velocity, we have all these random fluid velocities. And so what happens with dispersivity is that we chug along for a while at c equals to 0, but then our fast fluid flow paths start to show up, and we start to see a rise before the average velocity time, right? If we have a normal distribution, we'll actually see the midway point, we will see the average concentration occur right at the average velocity. And then we have our slow arriving fluid flow paths. And this point right here is C naught over 2, all right? And this happens at the same time lag, but now the fluid velocity is the average. All right. So dispersivity takes away these sharp edges and smears them out because of these early arriving flow paths and late arriving flow paths. Right? If we were to, let's consider another problem. All right, so let's think in map view. So we're looking down upon groundwater flow in a uniform flow field. So our water is moving at a constant groundwater velocity through a porous media from left to right here. And let's consider an injection of solute at an infinitesimally small point in an infinitesimally small time period. So here we are in map view, and I'm going to draw some axes here. This is X, and this is Y, right? And so at some time T0, and remember that we have groundwater flow, Q sub X moving in this direction. All right. Okay, so I lost some drawings. So recall that we're moving in a uniform groundwater flow field at Q sub X, right, which implies, an average velocity V sub X, which is constant. And we're looking down in map view and we inject, so this is at T naught and X naught, we inject a small point of solute, right? This little dot. Right, and if I was to come down here and draw a concentration contour across X, all right, so here, this is X, all right, and this is Y. And if I were to draw my concentration profile here along X, I would come along. So this is C, this is X. I would come along dot, dot, dot until I got to my point, and it would come up to C naught across the width of the point, and then come right back down, all right? So I have this small plug here along X. Now, it flows along with my uniform groundwater flow, but it's getting spread by dispersion. So now it's spread out, and here are some contours. It'll get spread longitudinally. It'll get spread in the X direction or the longitudinal direction, and it'll get spread in the Y direction or the transverse direction. So this is spreading in the longitudinal, and this is spreading in the transverse. All right. So if at this location, so this is T1, X1, right? And if at this location we were to draw our concentration profile along X, we would see that it looks like this. All right, and if we were to come sometime later, at some distance later, we would find that it had spread even more. So that if we came out here, the concentration now look like this. All right, so we go from a peak, we're getting spread out laterally. Now what's important is the integral from x equals a to b of c sub x dx. So the integral, the total amount of mass or the total area under these curves has to be equals. As long as we're not losing mass, the integral has to be the same. But we see that they're spreading longitudinally and transversely. And in general, we'll see that the rate of spreading, we will spread faster longitudinally than we will transversely. So the rate of spreading is not equal. And in general, longitudinal spreading, is much faster than transverse. All right. And if we were to think about uniform flow in a 3D field, we would see that there's spreading that's different along the flow path or longitudinally, transversely in the horizontal plane, and transversely in the vertical plane. And it turns out that dispersivity is super directionally dependent. It's a tensor, and it is, in fact, a really complicated tensor. We will reduce that tensor and talking about that tensor to thinking about essentially 2 or 3 components. Longitudinal spreading, so along the direction of flow, transverse spreading horizontally, and transverse spreading vertically. But we've had enough talk of dispersion for now. So I'm going to end the lecture here, but next time we'll get back into dispersion and talk about how we can combine dispersion and diffusion. All right. Thanks for your attention, and we'll see you guys later.